let us start. So we've been talking about scheduling, and we're going to continue that for part of the lecture today. But just a quick review. So one of the things we did finish up last time was a discussion of deadlock, and we talked about the banker's algorithm. And I just wanted to see whether there was any final questions, if there were any final questions on this. So the banker's algorithm, basically the idea is that all resources are allocated dynamically. Each request is evaluated, and it's only granted if some ordering of threads can actually complete afterwards. And the technique is basically kind of an extension of the deadlock detection algorithm we talked about, where you sort of, instead of the request less than or equal to available resources, you sort of substitute this max node minus alloc node is less than available resources. And this is not really complicated in magic. This just says assume that everybody requests all the rest of the resources up to their max at the point I look at the graph. That's all that's really saying. Okay? This will keep the system in a safe state, which basically says there's always some ordering that can complete. And as a result, we go through a series of safe states, and barring other problems, this system should complete without deadlocking. Can anybody give me a problem or two that might cause this banker's algorithm not to work? Yes?
We don't know what's the maximum resources available for each thread.
So we will assume that, okay, yes, if we don't know the max for every thread, it won't work, but let's assume that we know that. What else? Yes? So all it really depends on is it depends on threads releasing resources at the end of their execution. So if they end execution and don't release resources, you're right, that could be a problem. Oftentimes, operating systems will release resources automatically even if you exit without releasing them, but you'd need to make sure about that. What else could be a problem here? What happens if we run the dining lawyer's problem with one chopstick in the table? Not enough resources for anybody to run. Okay, so if you set your maxes too high, it's possible that this basically can never run. So that's another problem. Okay, were there any other questions on the banker's algorithm? I think we went through that in section last week too. But so you in theory could run the banker's algorithm through a series of requests and sort of figure out whether to grant or not. Okay. If you want to see some examples of doing that, you might check out a few of the midterms in the past, because that's occasionally been asked of you. Last time we started diving into scheduling, and basically the idea of scheduling is selecting a waiting process from the ready queue. That's the way we're going to zoom in on it. But scheduling is a more general term where we could for instance, decide how to schedule any resource or any thread's access to resources on waiting queues as well, but we're going to stick with the ready queue for now. We talked about two particular scheduling algorithms. Let me put these up here. First come, first serve, or otherwise known as FIFO, and round robin. So the good thing about the first come, first serve scheduling is it's really simple. Okay, if you're an operating system designer, you like first come, first serve because you don't have to work very hard. Okay. Problem, of course, is this has the convoy effect, which is short jobs get stuck behind long jobs, and then you got a problem, especially if a long job might take days or something, right? So that led us to round robin, which is kind of a generic way of getting short jobs to run sooner than they would if they were stuck behind the long jobs. Okay, and the basic idea here is really simple. We give a maximum quanta. 10 to 100 milliseconds is pretty standard today. And if a thread runs for longer than that, what we do is we preempt it, put it on the end of the queue, and we take the next one. Okay? And the good thing about this is, while it's more complicated, it does make sure that short jobs do get to run eventually. Okay? The con, of course, is that if you happen to have a set of jobs that are all the same length, then you're going to end up wasting time context switching. Okay? Now, maybe these jobs are all the same length, but they are incrementally outputting stuff, then, of course, round robin is going to maybe give you the feeling that all of them are running at the same time and therefore is good as well. So were there any questions on these two options? Because we're going to delve into a few other ones. Yeah?
From your graph you had up, it seemed that round robin could never be as good as first come, first serve in the best case, and it was usually about 50% worse.
You mean like this graph?
Yeah.
Okay.
So, I mean, you would think that in first come, first serve, on average, it would never be best and it would never be worse, so it would be around like the same as round robin.
Mediocre. We all say what? Yeah. So.
Like sometimes you would get small jobs going for big jobs, and sometimes you get big jobs going for small jobs, and in the end, it would kind of converge to around the middle, which is kind of what round robin is.
Yeah, except for the following. So I wouldn't necessarily say that first come, first serve would converge ultimately to be kind of in the middle, because it's those periods of time when a short job is stuck behind a long job which will continue to recur. And that's the annoyed user problem, right? Whereas the round robin doesn't have that annoyed user problem, because it doesn't matter how the jobs are submitted or in what order, and even over the long term, we still have less annoyed users.
Well, even then, like, I'm assuming, I guess, these long jobs are going to be either hardware interrupted and made to yield, or...
Not in first come, first serve. So that's the idea here is you run to completion or to the next I/O operation.
Okay, so there's, until you block, you run.
Yes.
Hardware.
Yep. Because remember, we've started this whole discussion with a graph, which maybe I should have put up here, of burst time versus frequency. For burst time on the axis, frequency on the y-axis. And the idea there was kind of short bursts are frequent and long bursts are not so frequent. And the reason the short bursts are frequent was because they come from people doing I/O, typing, whatever. And those are the ones that we'd like to somehow give precedence to not annoy people, right? Does everybody remember that a little bit? And so that was kind of what led us to reject first come, first serve, because it really didn't service well the short burst case. Okay? Now notice, by the way, that the results here are much more sensitive for the short jobs than the long jobs. Okay? Now, granted, there are cases of zero waiting time here, or zero, actually there are no zero completion time, but zero waiting time. Those are kind of anomalies, but if you look in here, the short job P2, which has only 8 units of time, has the most to lose, because we could go from 8 to 145 in the worst case. So that's a huge increase in total wait time. Whereas the long job, like P3 here, is pretty much insensitive to scheduling. Okay? Now, the other way to look at that is the long jobs, if we delay them a little to make the short jobs more happy, the long jobs don't notice because it's a small fractional increase in their overall timing. Okay, so by basically sacrificing some of the compute time for the long jobs, we make the short ones happier. Okay? Now, ideally, what we really like is we'd like to have first come, first serve ideal all the time, right? So, because this is always the best. If we were to sort jobs in some fashion that puts the shortest ones first, basically we win. Okay? And best first come, first serve is exactly what we show here. So shortest is first, and the next shortest, so on and so forth. And that has the best average wait time and the best average completion time. So we'd like to take the FIFO, or first come, first serve, and just sort things. That would be nice, wouldn't it? Because then we'd get the best of all worlds. Okay, now there's some problems with that, which we'll have to discuss. And that's kind of where we're going to come up today. So first of all, in order to do that, we've got to know something about how long the actual jobs are. Okay, in order to sort by job length, we actually have to know what the lengths are. And so there's something which is a guaranteed not to exceed idea here, shortest job first, where we have somebody with a crystal ball figuring out how big the burst times are so that then we can sort and put the shortest ones first and the longer ones last. Okay, and so that's not surprisingly shortest job first, SJF. Okay, but notice it's got an oracle here of some sort that's basically predicting. So we're going to have to deal with that. Now, the interrupt-driven version of this is what I'd call shortest remaining time first. And the only difference between these two is, in the case of shortest remaining time first, if I happen to insert a new job that's shorter than the one currently running, I will actually run the new job. Okay, whereas shortest job first, you could think it just kind of sorts the ready queue, whereas shortest remaining time first actually says, well, this thing's coming in as even shorter than the thing I'm running, therefore run it right now. Okay? And you can apply these to the whole program or bursts like we've been talking about. And this is actually really great for the short jobs because they tend to get in front, and it's, it basically gives you better than average response time. So this is going to be better overall than round robin, which is kind of a mediocre but not so bad way of making sure that short jobs eventually get to run without too much weight. Okay? Everybody with me on this? Now the couple of problems, well, the biggest problem with this is we need to predict the future in order to make this work. Okay? Now, one thing that I will tell you is that this is actually the best at minimizing average response time. Okay, so this is provably optimal, and so that's good. Okay, so even if we couldn't predict the future, we can at least use this as a straw man in which to basically judge whether a particular scheduling is good or not. Okay, so that's why we discuss it. And let's compare SRTF with first come first serve and round robin. So if all the jobs are the same length, what happens? Well, SRTF just degenerates into first come first serve. Why? If all the jobs are the same length, there's no sorting them. You start running a job, oops, it's now shorter than all the other jobs, so it'll run to completion. Then you take the next one and so on. So if all the jobs are the same length, SRTF just basically runs them in order. Now, on the other hand, if the jobs have varying lengths, then SRTF will put the short jobs first. And so you could kind of think that round robin is sort of like an approximation to SRTF in some weird way. It's not a great approximation, but it's kind of one. Okay? Because they both try to get the short jobs first. Let's see if we can see how this works here. So suppose we've got 3 jobs of interest. We have, actually, why don't you close that door because we're making a lot of noise here. Let's pull the little foot out. Maybe we'll open it up again at break time if it's too hot in here. There we go. So job A and B, they're very long. They run for a week. Okay, job C is a multimedia app, and what it does is it does some compute for a millisecond, accesses, say, a CD-ROM for 9 milliseconds, and then computes again, and so on. And you could think of this compute phase here as actually figuring out how to, figuring out what to access next. And then the I/O operation here is sort of 9 out of 10 milliseconds. Okay, and so in order to really optimize use of the disk, C needs to make sure that it gets to basically run the disk for 90% of the time, because that's optimal. A and B, ideally, to get the best throughput, they'd like to run all the time. Okay, and so now the question is, what does that mean? So if C basically uses 90% of the disk, A or B is 100% of the CPU. If we try to put them all together into the same machine, what happens? Well, once A or B gets in, it runs for a week. Okay, so I would say that the utilization of our disk just went to very low, right, 0. Okay, so that's FIFO is pretty not pretty good here. What about round robin or shortest remaining time first? Well, let's actually look at a timeline here. So here is an example of round robin with a 100 millisecond time slice. What you see here is that C gets to run for a millisecond, then it does its 9 milliseconds of I/O. Meanwhile, after that 1 millisecond, A runs for 100 milliseconds, B runs for 100 milliseconds, then C gets to go. All right, so what's the, what fraction of the disk are we using here? Come on, you guys can compute this. Yeah. Yeah. 9 201sts, right? Right, because we have 201, we have 100, 1 millisecond. So it's 201 milliseconds, and we get 9 milliseconds of disk time. Everybody with me? So we're at about 4.5% of disk utilization here. Okay, so that, even though this is a pretty standard thing, 100 millisecond slice time, we're not doing very well on the disk. So any of you actually been in a situation with a CD-ROM where you're trying to write something to it or read something from it, and because you had something else going on, it basically wasn't going very fast? Okay? That may have nothing to do with the CPU being busy other than the fact that you were missing catching the disk at the right rate. Okay? It's, you know, you have to catch it, say, every revolution, or, you know, if you miss a revolution, you start getting really, really low utilization. So how could we improve this? Well, we could certainly bring the round robin time down to a millisecond. Okay? So here we run, C runs for a millisecond, then it's going to be idle for 9 milliseconds while we have A, B, A, B, A, B, A, B, and then C comes along, then A, B, A, B, A, B, A, B, C, and so on. So what's the disk utilization now? Yes? Should be pretty close to 90%. Now, of course, there's some boundary effects, and who knows, especially since there's a lot of overhead here, right? There's a lot more switch time than there was before, so we really don't know whether we get exactly 90. I mean, it's highly likely we're going to get a little under 90 here, okay? And we're also switching a lot. This looks a little wasteful. I don't know if that looks wasteful to you guys or not. But now if we look at SRTF, that looks like an ideal, right? Because what happens is C runs for its millisecond, then A starts running, then C is ready to go again, so it's now the shortest remaining time, so it gets to run, and then A keeps running, and so on. And why do we keep running A instead of B? Yes?
Because the job size, A and B both take the same amount of time to complete one B, and since we have started computing A, it is the closest.
Yeah. So now A basically is shorter than B after the very first slice, so now A is going to go to completion. Okay? So this actually has a lot of benefits. First of all, we're going to get what kind of disk utilization? 90. And A, if it had any cache state that doesn't get disturbed by C, it'll get to keep it, right? And so this seems like a pretty good scheduling. It sort of gets us our 90% disk utilization and gets us our pretty close to 100% utilization for both A and B. Okay? Yeah. Oh, the drawback here is B would have to wait a week. Is that a good thing or a bad thing? Yes?
I think it could be a good thing because otherwise you have to wait like 2 weeks, like where both of them will kind of finish around the same time. You can kind of swap between both.
So this is one of those questions which may not have a real answer to it, right? It could be a good thing, it could be a bad thing. It depends on what your goals are. That's a great reason why it could be a good thing. It's a good thing because the average response time between A and B is better than if we swapped all the time. Remember, I actually showed you round robin last time with 10 100 millisecond jobs, and what you saw is the average response time was really bad because nobody was finished until like 991 milliseconds in. Okay, so from an average completion or response time, this is better. Now, if you're the person that started job B, you might be a little annoyed to be, you know, you went off for a coffee break and then it went into dinner and then breakfast and then dinner and breakfast and dinner and breakfast. And then sometime a week later you get to start seeing results. You might be a little annoyed. Okay? So, all right. Any questions on this? Now, the real question, of course, is let's suppose we really wanted to do SRTF. How do we do SRTF? Solve the halting problem. No, I probably, this is worse than the halting problem, maybe. Yeah, we need a crystal ball here, right? So clearly, at best, we're going to approximate SRTF. The real question is how to approximate it. Well, we might need some prediction technique. So one prediction technique that we could use is to try to build a model of the bursts and then use that model to sort the queues. Okay, so in general, we have the idea of an adaptive policy, where an adaptive policy isn't really guessing the future. Well, it isn't really predicting the future. What it is it's guessing the future based on the past. Okay, and that's a pretty time-honored technique. They even try to do that in the stock market, however well that works. The reason this idea might even sort of work is basically because programs have predictable behavior. So if it was I/O bound in the past, it's likely to be I/O bound in the future. If it's has certain cache behavior, it's likely to repeat that. Okay, so to the extent that programs are predictable, then we could actually use a model to maybe predict them. Now, of course, if computer behavior were completely random, none of the techniques we might come up with would work, but we would have other problems, like our memory system would be very bad because the caches wouldn't work well. Okay, so there's a lot of reasons why in today's computer age we depend on predictability crucially. That's a whole other philosophical topic. But so here is one option. We could build an estimator function. How many people have seen functions like this, right? This is where the predicted time for the burst is a function of previous bursts. Okay? How many have you people seen these before? Yeah. I mean, this is pretty common. So F could be many different types of things here, Kalman filters, whatever. There's whole classes you could take here at Berkeley on this kind of idea. Here's one that I'm sure you've seen. This is the exponential averaging idea, right? Where we say that the new estimate is the old estimate times a deweighting factor plus the new time that we've just observed times alpha, where alpha and 1 minus alpha add to 1, of course. And what this is this is a smoothing function, which I'm sure you've seen. It's a very simple time series. And notice that if these are our various prediction times, this smooth result is kind of what we get by the statistical averaging. And we could use that to predict what our burst times were. Okay, so we could actually attach to every job in the system sort of a filter to estimate. Okay, questions on that? Is it perfect? No. Is it good enough? Maybe. Okay. Here's another way to estimate SRT, or to approximate SRTF. It's called multi-level feedback scheduler. This one is very common. Okay, and the idea here is that rather than one ready queue, we're going to have n ready queues. Okay, and these ready queues are feeding into each other. So notice the top ready queue here has a short quantum like 8, and then we have a quantum of 16, and then maybe a FIFO for background tasks. And the question is, how does this work? The way this works is every one of these queues has a different priority. So the ones at the top are higher priority than the ones at the bottom. And each queue has its own scheduling algorithm. So notice that these are kind of round robin, and this one's a FIFO. And in some cases, the quantums are going up, like we've got here. And the basic notion here is very simple. Anytime you have a new job, and by the word job here, I'm meaning thread or process or whatever you're scheduling. We're kind of intentionally being vague there. We start at top. And then we let it run according to this scheduling algorithm. And if it turns out that the quanta runs out, so what do I mean by that? I mean I run for 8 milliseconds, and then I have to take the CPU away. At that point, we decide that this job is a longer running thing than we want at our top level, and we put it down to the next level. Okay? And if it expires here, we bring it down to the lowest level. So things that run for a very long time kind of fall down and eventually end up in the lowest level of the scheduler. Anytime you complete, you actually end up, depending on the scheduler, either back at the top or you kind of go up a level. We'll say back at the top here for a moment. So can somebody tell me why this kind of approximates SRTF? Why does this look like this might approximate SRTF, sort of? Go for it. We're sorting threads by previous history, yes? Yeah, so the shorter jobs are hanging out at the top, and the longer ones are hanging out at the bottom. Yep, go ahead.
So instead of perfectly sorting them, you kind of are grouping them into almost like the first level of a sort. You're grouping them into things under really fast things, medium things, and long things,
Yeah.
and then running in that order.
Yeah, so this is like a very coarse-grained sorting where we sort of have really fast, short things up top and longer things here and longer things down further. Yeah. So what kind of behavior do we get out of this thing? Well, assuming that we prioritize the top queue higher priority than the second queue than the bottom queue, do you see how shortest jobs kind of end up running first? Okay. So this is actually kind of a poor man's shortest remaining job first, and this actually, you'd find this in many operating systems. This is pretty common. The CPU-bound jobs just basically fall all the way down to the bottom. Short-running I/O jobs stay near the top. We have some details we could think about, like, for instance, how do we schedule all the different queues? Okay, so I've told you how jobs move between the queues, but the question might be if we have a bunch of queues, how do we pick something? Which queue do we pick something from? Well, we could pick something from the first queue, always, over the second queue, over the third queue. Okay, so we make the first queue highest priority, second priority, lowest priority. Problem with that, of course, is what? Yeah. Yeah, we got a starvation problem because the thing in the bottom never gets to run. Okay? The other option might be to give some fractional time slicing, where instead of a strict priority schedule, what we do is the thing at the top gets 70% of the CPU, the next one gets 20, the bottom one always gets 10, and as a result, even when you fall to the bottom, you still get some fraction of the CPU. Okay? Now, hopefully those of you that are thinking about this are like, well, how do I pick 70, 20, 10? How do I pick the quanta? How do I decide how many levels? Magic. Okay, if you were to actually look in the interior of a number of different schedulers in different operating systems, you'll see that they are approximations on top of approximations with hand-tuned parameters of all weird sorts. And so if you're wondering why your scheduler's behaving weirdly sometime, it's probably because it's behaving weirdly. Okay? And nobody could fully explain it to you. All right? Now, what's kind of interesting about this type of scheduler, which, by the way, is common, is you can do countermeasures on this. Now, what do I mean by that? Suppose that you're a long-running task that would like to get a lot of CPU. What do? You make sure you do a lot of I/O. Right? Because the more I/O you do, the higher up in the hierarchy you end up. And it's kind of interesting. There was some pretty clear examples. There was an Othello contest once that everything ran on the same machine, and actually what they did was the winning Othello game figured out to put a bunch of printfs in their program, and as a result they got more CPU time and therefore were able to beat their competitors. Okay? So some of this issue with schedulers is if you know enough about them, you can figure out how to game the system, and I mean that literally here. Okay? The other thing that's a little funny here is suppose that despite all of your tweaks in the scheduler, there's some job that just never gets to run because it's way down in the bottom and everybody else is getting to run. What do? Well, you could leave it there, or you could slowly raise its priority up. Okay, so there are Windows and several Unix variants all have sort of techniques whereby when they notice that something hasn't been running enough, they slowly crank its priority up until it starts running. Boy, is that another kind of, well, it's a heuristic. Okay, so I would say the state of scheduling is an interesting one when you have many jobs. Okay, any questions on this? Yeah. The question is, does scheduling become less important as multi-core CPUs become more prevalent? In fact, it actually stays as important or becomes more so, because if you have multi-core CPUs, you're banking on the notion that things you formerly ran serially are somehow parallelized, because otherwise you wouldn't get speed up as they added more cores. And so what that means is that the parallel schedulers that are trying, even within a single job, become extremely important to try to make sure you get that parallelism. So schedulers within tasks become important, and then scheduling between them become important to try to make sure that things that can use CPUs get the CPUs, and things that would waste them don't. And so I think it's as complicated or more so with multi-core. Okay, Administrivia. Midterm 1 is coming up. It's a week from Monday, 2 weeks from last Monday, 3 weeks from the previous Monday. It's going to be in 155 Dwinell. It's closed book, 1 page of handwritten notes, both sides. Okay, no microfiche, no magnifying glasses. Make sure you let me know if there's a conflict. Send me email. We'll consider conflicts. There's no class on the day of the midterm. As I've mentioned, I'll have special office hours. The TAs will probably too. The other thing is there's going to be a review session the Sunday before at 7, and we don't know quite where it is yet. It's probably in 306, but not sure. I mean, how many people would come to a review session if we had one? Okay. We're probably okay with 306. The problem with this room is it gets kind of hard to get a hold of late at night, because it's an institute room. Okay. Topics are everything up to the previous Wednesday, et cetera, et cetera. Any questions on the midterm? There are midterm 1 examples up. Anybody here looked at the examples yet? A few of them. There's also solutions. Anybody looked at the solutions? Sort of. Okay. Probably good idea to see what Kubatowic's exam looks like, just so you know. Okay. There's one little thing I wanted to mention. I put a posting on the news group. I don't know if people saw this, but there was a little bit of unclear specification, because people were told different things about whether they had to do in order or not with the communicator. So you're not actually required to get in order. Just hold on before you object here. You're required to make sure that everything that goes in goes out with some. So every speaker that sends something in, the result goes out with some listener, and you don't see any duplication of results, and the speaker's not allowed to return until the listener's actually listened. Okay, those are the main specs. If you think you have a solution that's going to be in order, and I define what I mean by in order on the news group very carefully, you should take a look, but it's basically, speakers are sort of looked at by the time in the order they enter the communicator as our listeners, and you match them up 1 for 1 in the way I say. If you think you've got a solution that meets those constraints, you can explain that in your design doc, and we'll give you some extra credit for it, but you need to make sure that the grader can understand, okay? So the auto grader will pass things that don't match the in-order constraint. That's what we decided to do, but you can get extra credit for your in-order solution. So hopefully everybody's happy with that. There is a little bit, so we were still having problems with the auto grader, so there was apparently a 3-hour period where people might have got, when was that? Yesterday afternoon, where Inst was playing with the auto grader, and you might have gotten some results saying you passed when you didn't really, and I think that Angela reran all those results, but you might want to just double check to make sure. Sorry about that mess. I mean, there was some weird thing that happened with the shell scripts that we have no idea. They've worked for 5 terms now, and the autograder has given us trouble this term. So, okay, I think that's all the Administrivia. Anybody else have a question? Okay, good. Everybody managed to get at least one result back from the autograder? Good. Okay. All right, don't forget to do your group evaluations, okay? Try to do those by tomorrow at the latest. because we want you to do those. Okay. So let's finish up scheduling fairness. So what about fairness? We kind of indicated that fairness is not always what you want. And part of the reason is you don't always know what fairness means. But so for instance, a strict fixed priority scheduling between queues is unfair, run the highest and the next, et cetera, because the long-running jobs may never get CPU. There's actually a tale which I believe is true but maybe a little apocryphal, but that when they finally shut Multics down, there was actually a job that had been there for 10 years and not run. Now, perhaps that's apocryphal, but you get the idea. So, and this basically leads us to making sure that somehow the long-running jobs always get some CPU, and our fractional idea is one of them. But notice that if we took the multi-level scheduler as an approximation for SRTF, and then we let the low levels get some guaranteed CPU, we've kind of traded off average response time. You could say SRTF kind of gives you average response time at the expense of fairness. And so we can kind of decide how to tune those. And that's, again, a little bit about tuning. How do we get full fairness? Well, give each queue some fraction of the CPU. So I said that as well. And then finally, what happens in Unix oftentimes is they combine a multi-level scheduler with something that tries to increase the priority of jobs that doesn't get service. OK. Now, I want to give you another alternative to make sure that everybody gets some CPU time. And this is going to be important because you get to implement this in your next project. It's called the lottery scheduler. And the idea behind the lottery scheduler is that every job gets some number of lottery tickets. And the more lottery tickets, kind of the more chances you have to win. Okay? And the idea is that at each time slice, you randomly pick a lottery ticket number, and the job that has the lottery ticket wins and gets that time slice. Okay? So you can see that somehow the CPU time is proportional to the number of tickets. Right? The more tickets you have, the more chances to win, and therefore the more CPU time you get. Now, how can we assign tickets? Well, to get something like SRTF, we really want short jobs to have more tickets than long jobs. Okay? And to avoid starvation, we want to make sure that every job gets at least one ticket. Okay? Everybody, that makes sense to everybody? Now, of course, probabilistically, this last statement is true. You could make this absolutely true by using a pseudo-random function or something that made sure that you went through every ticket once before you went through tickets again. Okay. Now, the advantage over strict priority scheduling is this behaves gracefully as the load changes. So as you add or delete jobs, then everybody kind of proportionately slows down or speeds up, and you still make sure that there is no starvation. Okay, and I can give you some very specific examples here. So suppose that we give short jobs 10 tickets and long jobs 1 ticket. Then suppose we have one short job, one long job. Then basically the short job gets 91% of the CPU. The long job gets 90% of the CPU. Okay, you guys can figure out, right? 1 over 11, 10 over 11. Okay, good. If we have 2 long jobs, they each get 50% of the CPU. If we have 2 short jobs, they each get 50% of the CPU. If we have 10 short jobs and a long job, then each short job gets 9.9% of the CPU, and each long job gets 0.9% of the CPU, or 1% basically. And vice versa, if we have 1 short job and 10 long jobs, then we get kind of 50% for the one job and 5% for each of the long ones. Okay, so notice that nobody here is 0, although this long job is hurting a little. Okay, but we managed to make sure everybody makes some progress. Now, if there's too many short jobs, then, and this is the case where there was a lot of short jobs relative to long jobs, then basically what happens is some of the jobs get pushed out. So it's like starvation. They get to run, but they're running really slowly. And if you're on a machine with a load average of 100, nobody's making much progress. I mean, that's just, no scheduling is going to do well. Okay, are there any questions on this lottery scheduling idea? Yes? Is this implemented in the wild? I don't know I don't know whether anybody ended up actually doing this. Mostly the multi-level scheduler is pretty common. Yeah.
If you like run out of random numbers, if you're using like the ones that are built into your system.
So could you run out of random numbers? Well, fortunately, that's a whole other topic, but fortunately you can build with shift register techniques, you can build any random number generator up to the bit width of your computer without any problem. So those are pretty simple to do. So they don't have to be truly random, right? It has to be just random enough. Statistical randomness here is not really required. Yeah? How do you know if the job's going to be short or long if you give out the tickets? Well, this lottery scheduling, as I presented it, somehow you know. So now we're back to figuring it out. So you could build something like the longer you run, you start taking tickets away, or, you know. This is, I'm leaving this to the reader to figure out how to impose a prediction technology on top of this. That's good, but that's a good question. I didn't tell you how to do that here. Okay. So let's sort of finish up scheduling topic here. So how do you evaluate a scheduling algorithm? I already indicated to you that it can get pretty complicated in the wild. There's a lot of knobs that people turn. And, you know, what do you do? Well, we could try to do a modeling scenario where we take a predetermined workload and we somehow model the scheduler and compute the performance of each algorithm, you know, each scheduling algorithm for that workload. Now, the problem with modeling is coming up with a mathematical description of an ad hoc complicated scheduling algorithm is not an easy thing to do. Okay? Maybe the lottery scheduler is something that you could model pretty easily, but you know, the multi-level scheduler is probably not something you could model mathematically easy. Okay? Now, another thing you could do is you could build a queuing model. So if you have multi-level queues and you know, somehow drive that with your workload, some sort of simulator, and maybe you could make that work. So queuing model is a specific type of model, and maybe for a multi-level queue you could come up and make it work. Probably what you're really going to do is you're going to simulate somehow. Okay, so simulation is the most general, and what you do is you build a system that lets you run the real applications in simulation somehow, and you try against the different schedulers, and you get performance statistics out, and you pick the one you like. Okay, and you could even imagine you run a simulation and then you run it with a bunch of different knobs, and then you pick the knobs you like best. These are all options. Now, why do I say simulation instead of just putting the algorithm into a real operating system? Well, it's possible that what you could do is take the applications and reduce them down, rather than instructions, you could reduce them down into, you know, the sizes of the bursts and how much I/O they do. And so your applications could be represented a little more abstractly with some parameters like, oh yeah, they do a burst of 10 instructions and then this and so on. And so that you could run through your simulator without actually having to implement a real operating system, which could get messy. Okay, so that's why I use the word simulation here. Okay? Of course, the fourth option, which I don't mention here, is, you know, you have the Linux kernel, you release the new scheduler, you wait till the complaints come in, you tweak it, right? Or in the case of Windows, what happens is they release it, it crashes a bunch of things, they get the feedback automatically over the net, and the next patch has a different scheduler in it or something. Who knows? Okay. So, a final word on scheduling. When does it really matter what scheduler you have? It matters when there aren't enough resources to go around. If you have only one job running on a machine, who cares how your scheduler works? That job is happy, right? It's when you have 1,000 jobs, it doesn't work at all. Or if you have 10 jobs, well, when you're in the medium range, then your scheduler might really matter. So you might ask the question of when do you tweak your scheduling or versus buy a whole new machine? Okay? Now, it's hard to believe as students, but there will be a time in your lives not too long from now when you can easily make this decision. Well, this isn't working very well. I'm going to buy a new machine, okay? And you might ask when. Well, you might want to buy it when, for instance, it could pay itself in improved response time. Okay, and you know, maybe what you get by not having good response time is productivity problems, or maybe more electricity cost, or whatever. And you've seen this graph before. This is the generic utilization versus response time graph. Remember this one? You've seen it at least once this term. And notice that I have contended that all situations where utilization is an issue here, you have a graph where response time kind of, as you approach 100%, starts rising drastically. Okay, so we have this nice region here where you kind of have the linear growth region, and then we've got this sort of fall off the world kind of response time region. And there's many reasons for this. We'll talk about a few as we get into paging and also as we get into queuing. But this is a general statement. And you might say, when do I buy a new computer? Well, I buy a new computer when I'm out of the linear region and in this knee of the curve where things are really falling apart. That might actually be a good time when you know that you don't have enough resources and you need more. Okay, because you certainly don't want to be operating at 100%. Okay, and maybe when you're down in this region, it makes no sense to spend the money on a bigger machine. Okay? Good. Any questions? All right, so what we're going to do is let's take a break, and we'll pick up in about 3 or 4 minutes, and we'll switch gears again. All right. So let's switch gears a little again. So we've been talking about virtualizing the CPU with our scheduling algorithms. So let's broaden our horizon to virtualizing other things. And the physical reality is basically different processes and threads share the same resources. Now, we've been talking again about the CPU, but for instance, memory is a resource they share, disk, network, keyboard, mice, you have it. These are all things that need to be shared. And the question is sort of, well, we've talked about CPU. If we're going to move on to memory, why do we care about memory? And the answer is, well, memory holds the complete working state of the process. So, the CPU is like a transient thing. The memory has the state. And so that's actually, you could kind of say the process is the memory in some sense, plus its TCB and so on, right? And so, consequently, we have to be very careful not to let the wrong sort of control happen here. So we can't have different threads from different processes have access to memory. We talked about that as a protection thing earlier. It's also kind of, it's about avoiding chaos and incorrect execution. Now, you could kind of say, well, there's a physics argument here, right? Two things can't be in the same memory at the same time, but perhaps that's going a little bit far. You probably don't want different threads to have access to each other's memory, except if they're explicitly needing to share. So that would be different threads in the same process. Maybe they need to share. Different threads in different processes don't. Okay, and so this is a question of how do we virtualize the one DRAM that we've got to kind of give us a better controlled environment. Now, if you remember, we sort of had this picture of single and multi-threaded processes. And here, we've got the process boundary, which represents an address space. And within that address space, we've got multiple threads and multiple stacks and multiple registers. And they're all kind of sharing, but these two processes are not. Okay, and so threads are the concurrency portion, and the address spaces are the protection and the state of the system. And let's now dive into a little bit how we protect memory. Okay, so what are some important things we could hope to get from multiplexing the memory in a controlled fashion? Well, one thing is controlled overlap. Now, what do I mean by that? Well, different threads should not collide in physical memory. So we need to make sure that, basically they have at least some state that's separate, like the stacks and so on. So that's important. And we want to be able to have controlled overlap when it's useful. So if two threads are actually sharing stuff, then we'd like to have overlap in the same address space. Okay. Translation. Here's another aspect we might consider. So here is that we might want to be able to translate from one address space to another one, in particular from, say, virtual to physical. You remember that little spaghetti diagram I put up at the beginning, first lecture or whatever. I'm going to bring that back, which is actually showing us on the translation that's happening in hardware. And when there is translation, processors basically compute or access virtual addresses, and the physical memory uses physical addresses. And we use the translation to kind of control that mapping. One other side effect, by the way, that's useful of translation is we can give a unified view of memory to programs regardless of how many there are. So we might have 12 different things running simultaneously, 12 different processes, and every one of them can have an address 0 with translation. Okay, we're going to show you in a moment that that actually makes the job of the linker a little easier because it can link one process regardless of the number of things that are going to be running at once. Finally, obviously there's a protection angle here, which is we're going to prevent access that we don't want to allow. So we're going to prevent access to private memory of other processes. And we can also do some other interesting types of protection, which we're going to start talking about. Like, for instance, we can say this region of memory is read-only. So if a process or if a thread within a process tries to actually write that region of memory, what happens? Well, they get bounced. Okay? What's a good example of read-only that we might want? Yes? Kernel, definitely. Okay, in fact, the kernel might even be read-none, right? What else might we want read-only for inside of a process? Yeah. Code. Okay, assuming we don't have self-modifying code, we probably want to protect the process from writing to itself by accident and screwing its code up. Okay? All right. So this controlled overlap, translation, protection, these are all kind of things that we're targeting here. Are there any questions on these? Now, let's go at this a couple of ways. I'm gonna go at several of these pieces, the overlap, translation, and then eventually protection, with and without hardware. Okay, so we're going to assume that we have different types of systems, and we kind of look at the different advantages here. So to do that, I want to talk about a binding of instructions and data to memory, which is something that you've all done many times but probably haven't thought about too much. And so the idea is that you're going to choose addresses for instructions from the standpoint of the processor. And let me just show you, I'm going to subject you to some assembly language here for a moment, but here's an assembly language program where we have some actual code that's doing load from a data region. It's doing a jump and link to some procedure down here, and then we eventually return, and then there's a loop that does some stuff. And then up here we have a region of memory that's just got data in it. So here's some instructions, here's some data. And notice how there are no actual addresses here. Okay, there are no addresses. All there are symbols. Okay? Now, part of what has to happen in order to allow this code to run is we have to produce actual machine code that can run on the machine. Okay, and if you take a look here, notice that now, rather than labels, I've actually got addresses. So this, this start load word is actually at 900 hex. And the load word is actually an 8C20 followed by an offset, which it turns out points at the data. So if I were to take this assembly language instruction, turn it into a machine language instruction, this is what I'd get for MIPS. Okay, and this 00C0 is actually 0x300 shifted over by a couple of bits. Okay, so you don't have to think about the exact details here, but just know that before we can run this program, it has to be turned into something like this, and we have to bind all of the instructions and data to specific addresses in memory. Okay? I mean, what else do we have here? Notice this is jump and link to the check it routine, check it 0xD00. It turns out that if you shift that a couple of bits over, you end up with 000340 offset in a 0C, which is a jump and link, da-da-da-da. Okay, so this is what the assembler and linker phases are actually doing. Everybody with me on that? So part of making a program runnable is choosing the addresses that it accesses. And can we put data 1 or start or whatever at different addresses? Sure. Compiler linker just could put them anywhere it wants to, as long as it comes up with a self-consistent program when it's done. Okay? When do we do this? Well, that gets kind of interesting. We could do this at compile time. We could do it at load time. We could do it at execution time. Okay, so this binding of addresses doesn't necessarily have to happen at the very beginning. It might wait until the very end when it's about to execute before it binds. Okay, and that's what we're going to talk a little bit about here. Of course, related to this is the question of which physical memory locations hold particular instructions or data. These addresses may be virtual or physical. I haven't quite shown you different architectures yet, but in a machine that has translation that we just talked about, these are actually virtual addresses, which then get mapped to DRAM somewhere. In a machine that doesn't have translation, these might actually be the physical DRAM addresses. Okay? Now, let's take a look at, this is a figure right out of your book, at some of the things that go between you writing a program and it executing. Okay? So you take your program, you might compile it, let's say GCC. You might have to link it with, say, LD, and you might, at execution time, you might have to link in a bunch of dynamic libraries. We'll talk about each of these. So here's your C program. You compile it or you assemble it if it's an assembly program, or if it's Java, maybe it goes through a just-in-time compiler. You end up with some object module. At some point, it gets linked with other modules, and you end up with a linked program, which is loadable. At that point, it gets loaded, and maybe it's system libraries are there in the kernel and other things that are ready to work with. And then at some point, it may be that there's dynamic libraries. And in that case, as the program's executing, it's actually dynamically linking in libraries that happen to already be there in memory. Okay, and so it turns out in some instances, it might be until the very end here before you have all of your addresses bound. Okay. Now, let's talk about dynamic libraries, because I'm sure, how many people are aware of dynamic libraries? Okay, so these are the, you update your DLL files and your machine no longer works properly, right? This is a pretty standard problem. What are those things? These are dynamic libraries. And what they are they are library routines that are loaded into memory, and multiple programs can be using them simultaneously. So rather than linking, say up here, actually linking all of the libraries into every image, and then when you load them in memory, every loaded process has a copy of the same instructions. What we do with a dynamic library is we have one copy of the instructions, and we actually link it into each program that's running. Okay, and how that actually happens is typically there's a stub that's in the program, and as soon as you try to execute it, that stub goes off and does the linking, changes the addresses, and then starts executing. Okay? Any questions on this? So the point of this is that the binding of instructions and data to addresses can happen at many points in the system. Okay? And we can actually make use of the fact that a modern system binds at many locations to actually play with what kind of hardware support we're going to provide. And that's going to be kind of our next topic, both this time and next time. So if we think back to unit programming, where there's one process, no translation, no protection, application always runs at the same place in physical memory, application has access to all addresses, well, that would look like this. Okay, here's MS-DOS. The application is at some point in memory. The operating system is at some other point. All of the 32-bit addresses are in theory valid, although some of them may read or write DRAM that doesn't exist. And the application's given an illusion of a dedicated machine by having a dedicated machine. Okay? So this is kind of, pre-multi-programming. Of course, this doesn't help us much with more than one thing at once, so let's move on. So let's look at the first version of multi-programming of interest. And this, by the way, is sort of what MS-DOS did and other things, early Macintosh. So this didn't have any translation or protection. So somehow we got to prevent addresses from overlapping. So what do? We actually use some combination of the loader or linker to change at bind time all of the addresses so that the application 1 can run from a base of 0, and application 2 can run from a base of 0x2000, 20,000. Okay, so this is actually, as the thing is being loaded, we're translating all the addresses so that the thing can run at that part in memory. Okay. Now, I see some people shaking their heads. It turns out this is not too hard to do, because what you do is actually your object code is relocatable, and so it's very quick to go through a single pass-through and do the right thing. But does everybody see how this could allow these two things to at least coexist? Not with protection necessarily, yeah. Well, yeah. So what if application 1 starts overwriting application 2 or vice versa? Yeah, they overwrite, right? There's no protection here. So what we're starting with is trying to get some sort of multi-programming here. Okay, and the first thing we had to do is make sure our addresses don't overlap. Because if application 2 was also written or linked in a way that had to run from 0, then application 2 sitting up here isn't going to work. The best we could do is somehow put 2 and 1 on top of each other in memory, which we can't do, right? That's the whole physics thing. So this is the best we can do if we want these two things running at the same time. Okay? Now, of course, bugs in any one of the programs or the operating system overwrite each other. You don't lose. I mean, you lose. Nothing you can do about it. So what could we do to add some minimal hardware to fix this and give more protection? what do we want to do with application 2 to prevent it from messing up application 1 or the operating system? Think simple. Don't think complicated. Yes? Yeah, exactly. Limit the range of addresses we let application 2 use. Rather than giving it access to all 32 bits worth, we sort of limit. Okay, so, oops, sorry about the bug there. So what we do is we basically have a base for application. So these are two registers, base and limit. Application 2 has a base register, which is 20,000 hex. It has a limit register, which is 10,000 hex. Okay, or that's yep. And then the idea here is that application 2 is allowed to use any addresses from 20,000 up to 30,000. And as long as it stays in there, it's okay. But if it tries to access addresses outside, then it faults. Okay, that's actually pretty simple hardware. 2 registers. Okay, everybody with me? Now, of course, whatever scheduler we've got, when it's doing switch, it's going to have to change base and limit every time it lets a different app run. Okay, so when it's switching between this application and this one, it needs to be switching base and limit as well. Okay? Questions? Simple. Okay. Now here's what the hardware might look like. So now we can imagine, so this is one option. So now let's look at a different option, which is related. Okay, and the related option will be, suppose that we don't want to have to actually have the linker bind addresses uniquely depending on where we are in memory. So let's instead let application 2 be linked as if we're going to run at 0, but we're going to put it at 20,000. Okay, what do we need to make that work? Yes? An offset. Okay, what if that offset's just our base? So here's the hardware we could do to basically allow us to put application 1 and 2 linked as if they lived at 0, but in different parts of memory. Basically what happens is addresses coming out of the CPU, the base is added to them before they go to the DRAM, and we just check the limit register. Okay, so this is the simplest type of translation and protection hardware we could come up with. And this actually gives us pretty good protection and allows us to move applications around in memory without actually having to relink them. Okay? So this is the simplest form of dynamic address translation. Questions? This seem pretty obvious to people? Okay, now notice that we took a kind of a paradigm shift from here, where these have to be linked to fit in a specific part of memory, to here, which this is actually a virtual to physical address translation. I didn't add a lot of hardware, but I put a little summer in there, and suddenly I'm changing the addresses. In fact, you could say that this is a very primitive form of segmentation, where the segments are continuous from a base up to a limit, and they have to be continuous in memory. Okay? And we let the user read and write as long as they stay within their segment, and if they try to go outside the segment, well, what's interesting here is, assuming they can't use negative addresses, they can never get below their base. And we force, and if they try to go above their base, the limit will catch an error and they'll be toasted, and so we're good to go. Okay? Now, what's interesting is you can take this idea and very easily generalize it. So if you go to the x86, for instance, there's actually a bunch of segment registers. And you might get something like this, which is use the ES segment register :BX as an address register, and take what's at that address and put it in the AX register. So this is like a special load where we're using a particular segment and offset. What does that mean? Well, that means depending on what we put in the instruction for ES or whatever, we're actually picking a different base limit combination. Okay? So, what are some problems with this? Well, this segmentation model seems good, except notice what happens. So we're going along, and the operating system puts process 2 here and 5 there and 6 there, and then process 2 ends, and it puts process 9 there, and then process 10 comes along, and then, I don't know, process 5 ends or whatever. What are we fighting here? Fragmentation, right? So the problem with this type of segmentation technology is we're going to have to, ultimately, to deal with fragmentation, we're going to have to start moving things a lot. We're going to be copying from one place to another. Does everybody see that? So this sounds good until you start having many processes coming and going, and then you got problems. Okay. So, not every process is the same size. Memory space becomes fragmented. We have to deal with it. It's very hard to do inter-process sharing here. Why is that? Because right now we're sort of forcing processes to stay within their segment. So if we want process 9 and process 5 to talk to each other in shared memory, we have no way to do that. Yes?
So would you not be able to have a process use like a large portion of the memory?
Yeah, well, if you want to have a process use a large portion of memory, you've got to somehow squish it aside. I mean, you have to find a large portion of memory to have it use it. Because the way that we've set this up is your segments are actually representative of real DRAM.
But like I was talking about, like you have the base and offset, or like if you like so, can you only have this, or never mind, I guess if you can take up 2 segments.
Yeah, you're starting to run into some of the obvious limitations of this, right? Now, the way we could do sharing is by having more than one segment register, and maybe one segment's a sharing segment and the other is not. But this issue of large chunks of memory, unfortunately, we're basically forced to find a large chunk of DRAM in order to have a large chunk of memory. It's just kind of what the way this is. So every process that's running has to have enough physical memory here as well. So this is a little problematic. If we try to shove too many things in there, even if a lot of them aren't running, we don't have any technology for dealing with that. So how could we fix this idea? Like, how could we have more processes than fit into memory run? What would we have to do? Yes?
Wouldn't we just copy only the segments that we
So what do you mean by copy only the segments we need?
like we could split up, say like I'm assuming that we know the PC counter at whatever instruction process is.
Yep.
So when we swap it out,
You just back up there. You just said swap out. So we need to be able to potentially take something and put it somewhere else so that we could use that memory for somebody else, right? So the word swap that you just sort of blithely threw in there is not in this model, but we would need to be able to swap somehow. And where do we swap to? I guess we copy to disk or something in order, sounds like a good idea, right? In order to make this work. Now, unfortunately, this basic segmentation model still has fragmentation. And the bottom line problem here is processes are all different sizes, and we need to somehow play Tetris and fit them all into memory, okay? And that's just a bad idea, because we know the fragmentation is going to get worse over time, okay? So let's suppose, going further, we want to do better than that. So we'd like to run multiple applications in a way they are protected from one another. So what are our goals? We want to isolate processes in the kernel from one another. Okay, we figured that out. And we want a flexible translation that, 1, does not give us fragmentation, 2, gives us easy sharing, and 3, maybe allows us to have only part of the process in memory at any one time. Okay, because basically of these 3 things here, doesn't lead to fragmentation, allows easy sharing, and only part of the process in memory. This doesn't have any of those. Okay? The only way we even get sharing is if we somehow have more than one segment per process. Okay, so what do? We need some hardware mechanisms. So we need some general translation mechanism that's flexible enough to fit physical chunks of memory into arbitrary places in the user's address space. It's not limited to a small number of segments. And we could think of this as providing a bunch of pages of memory that we can use in flexible fashion. Okay, and we'll talk about what a page is in a moment. but think of it as a fixed size segment. Okay? And we're ultimately going to need to protect our translation in a way with dual mode operations such that the user is not allowed to change its translations, otherwise we don't get protection. Okay, now that base limit pair I told you about, so those clearly had to be protected so that only the kernel could modify the base and limit pairs. We're going to have to keep that idea going forward. All right. You've seen it. Okay, now I didn't really push at this too hard. And this diagram, actually, if you looked at this too closely, you'd kind of see some holes in it. For one thing, the way I'm implying here is that each thing, code, data, heap, stack, are all translated kind of en masse independently. Okay, and of course, we don't want that because now we get the fragmentation and DRAM problem. So we're going to want to make sure that every one of these chunks in the DRAM are all exactly the same size, regardless of how we want to use them. Okay? But basically, what we want is we want a general translation mechanism that can basically take anything from here in some user program and map it to anything in the DRAM, and anything from this user program map it to the DRAM, and do so flexibly. Okay? How do we do that? Well, first of all, we have to have some hardware, often called a memory management unit, that basically takes addresses coming out of the CPU and turns them into physical addresses. And so what we're going to look at for the remainder of the hour here, very briefly, is what does this MMU do? And we'll pick this up next time. Oh, and by the way, in theory, you can have the CPU go to untranslated addresses by going around the MMU. So what's an address space? So this is basically the set of addresses the process sees. Every process and the kernel have a different address space. Okay, so you could say that there's two views of memory in this system. One is the view from the CPU. Those are the virtual addresses. And the other is the physical address view. Okay. Translation is going to help us for lots of reasons. It's going to help implement protection, as we've talked about, because if task A can't be mapped to the same memory as task B, then there's no protection problem because they can't overwrite each other. And the other nice thing is basically with translation, we can make sure that everybody is linked exactly the same way to the same address space. Okay, so you always start at address 0. So let me show you a typical translation. We'll go a lot more into this next time. But for instance, here is an example of how translation works in several 32-bit processors. We take our address. Here's 32 bits. We take a page is basically going to be a unit of memory. In this case, with 12 bits, it'll be a 4K page. And the page structure here, this page table, is actually a translation table that's kept in memory. And what happens is the hardware is going to take this 32-bit address. It's going to start with the first level index. It's going to look up a page table entry for the first level index. So this 10 bits gives us 1,024 entries. We'll take the first entry. It's going to point to another page table, which we take the second page table index. That's going to give a second one, which then will point to an actual page that's 4K in size. Okay? And so the little blue bubble, remember the little blue bubble here? Okay, these blue bubbles actually are page tables like this in memory, one for every process. Okay? All right, how do we change address spaces when we change the process? We just change the pointer to the top level page table entry. Very simple. Okay. Now, don't worry about, we'll go in much greater detail about this next time. So let's finish up. In conclusion, we talked about, finished up scheduling. We talked about shortest job first and shortest remaining time first, which is a nice ideal that we might shoot after. This is basically run whatever job has the least amount of computation to do. And it's kind of optimal in an average response time standpoint. And we showed you how to approximate that with multi-level feedback, which is pretty common. And we talked about lottery scheduling. So I would say both multi-level feedback and lottery scheduling are ways of approximating shortest remaining time first. Okay? And we talked a little bit about how you'd evaluate actual mechanisms. So finally, we started talking about resource multiplexing. We're focusing on memory. We talked about controlled overlap, translation, and protection as 3 things we'd like. We showed you some very simple protection through segmentation, and that unfortunately has some problems like, running out of memory and having trouble basically dealing with fragmentation and so on. So we started on the path of a full translation mechanism called a memory management unit. And what we're going to do next time, we'll talk about dual mode as well, we're going to see, okay, if we've got a memory management unit, how might we actually structure our page tables and why? So that'll be our topic for next time. Don't forget to turn your projects in tonight and your reports, and do your evaluations tomorrow.